my dear students. In the previous video, we have discussed about defining the inner product in terms of the norm in the case of the special real inner product spaces. A similar definition can be defined in the case of complex inner product spaces as well. So, which is be done. So, which can be stated as in the case of complex inner product space, the real part of inner product xy should be equal to 1 by 4 times norm of x plus y the whole square minus norm of x minus y the whole square. And imaginary part of inner product xy should be equal to 1 by 4 times norm of x plus iy the whole square minus norm of x minus iy the whole square. So this is the definition. So we have to prove this. Let's get on to the proof. We already know that 1 by 4 times norm of x plus y the whole square minus x minus y the whole square should be equal to 1 by 4 times inner product x plus y minus x minus y inner product, which by simplification is actually 1 by 4 times we have simplified in the previous lecture, which is inner product yx plus inner product xy plus inner product yx plus inner product xy. This is what we have simplified in the previous lecture. So which should be equal to 1 by 4 times 2 times inner product xy plus inner product yx. Now we can cancel 2 and 4. So by simplification we get the answer as 1 by 2 times inner product xy plus inner product yx. Now we have defined this on a complex inner product space. So inner product yx by definition can be written as inner product xy conjugate. So this is actually 1 by 2 times inner product xy plus inner product xy conjugate. Now for a complex number, a plus a conjugate is equal to 2 times the real part of a. So using that we have 1 by 2 times 2 times real part of inner product xy. So by cancelling that we get real part of xy. Okay, so in the case of complex inner product space, this is actually equal to real part of inner product xy. But in the case of real inner product space, this conjugate is actually equal to inner product xy, because for a real number its conjugate is same as the number itself. But in the case of complex number, a number plus its conjugate is 2 times the real parts. That's the only difference. So we have established the first part of the proof. Now moving on to the second part. So in the second part we have to find the value of imaginary part of inner product xy. So we take the right hand side. So 1 by 4 times inner product x plus iy the whole square minus inner product x minus iy the whole square should be equal to 1 by 4 times norm can be written in terms of inner product as inner product x plus iy minus inner product x minus iy x minus iy. Now this can be split up into two parts. So if you write, we can write it as split into two parts as inner product XX, inner product XIY, and inner product YIYX, and inner products IYIY by repeating applying the properties of the inner product. So we can write that as 1 by 4 times inner product. So this should be, if we split up this should be equal to inner product x comma x plus iy plus inner product iy x plus iy minus of inner product x comma x minus iy, and there's a minus, if we can take outside, minus iy comma x minus iy inner product. So this is the answer. So this should be equal to 1 by 4 times. Now we can actually, this can be written in the reverse in terms of the conjugacy. So this should be equal to inner product x plus iy x conjugate. Similarly here also inner product x plus iy conjugate minus, similarly here also x minus iy x conjugate minus x minus iy conjugate. Now this can be written as, if you can split up the whole thing, this should be equal to inner product xx conjugate, which is actually inner product xx itself. So inner product xx plus, next is inner product iy x conjugate plus here also inner product x iy conjugate. Iy conjugate, which is inner product iy minus, this is inner product xx conjugate, which is actually inner product xx minus, next there's a minus, so minus times minus is plus, plus inner product iy x conjugate. Next there's a minus times minus plus inner product x iy conjugate. So plus inner product x iy conjugate. Next there's a minus times minus plus, plus times minus is minus, inner product iy conjugate, which is inner product iy itself. So this is the answer. Now we can clearly cancel inner product iy plus and inner product iy minus. And similarly, we can cancel inner product xx and minus inner product xx. So this should be equal to 1 by 4 times inner product. Now this can be written as, the first term is written as same, inner product iy x conjugate. Now this can be reversed, inner product iy x, because the property of inner product x iy conjugate is inner product iy x. Plus similarly here also, and next part inner product iy x conjugate. Now this part can be written as in the previous case, which can be written as inner product iy x. Now this is actually 1 by 4 times 2 times inner product iy x the whole conjugate plus 2 times inner product iy x. Now if we can take 2 outside and cancel 2, so this should be equal to 1 by 2 times inner product iy x conjugate plus inner product iy x. So now by the property this can be taken outside, or if you move this, this can be written as inner product. The first part by definition should be equal to inner product xiy if you reverse it. And similarly, if it in the case of the first component, you can take I outside, so I times inner product yx, because inner product is linear with respect to the first component. Here also you can take the conjugate of I outside, because inner product is conjugate linear with respect to the second component. So this can be written as 1 by 2 times I conjugate times inner product xy plus I times inner product yx. Okay, so 1 by 2 times. Now this can be written as inner product yx or xy as well. So this can be written as I conjugate is minus I times inner product xy plus I times, this is actually can be written as inner product xy conjugate, because inner product yx is xy conjugate. Now you can take I outside, so this should be equal to I by 2 times inner product xy conjugate minus inner product xy. Okay, so this is actually the difference between a complex number and its conjugate. Now for convenience, we multiply this numerator and denominator by I. So this becomes I square by 2I times inner product xy conjugate minus inner product xy, because we want to get an exact form, that's why. The I square is minus 1, and if you multiply this by minus 1, this minus and plus interchanges. So 1 by 2I times this becomes inner product xy minus inner product xy conjugate. Now this is actually a complex number along with its conjugate divided by 2I. So if a plus ib is a complex number, a plus ib, a minus ib is conjugate, then b, the imaginary part, can be written as a plus ib minus a minus ib divided by 2I. We can write as this, or a complex number z minus z conjugate divided by 2I is actually the imaginary part of that complex number. So here z, this is of the form z minus z conjugate divided by 2I. So which should be the imaginary part of inner product xy. So we have started from the argument that 1 by 4 times inner norm of x plus I by the whole square minus norm of x minus I by the whole square. So then we have proved that we should be equal to imaginary part of inner product xy. So we have established the relationship connecting real part of inner product xy with respect to the norm and the imaginary part of inner product xy with respect to the norm. So we have successfully established these two relations in the case of complex inner product spaces. Sometimes these relations, these two relations, are called polarization identity. These two relations are called polarization identities. And this ends the first section of the module 1. You have an exercise assignment. Question number 1 to 10 of page 135 of the textbook, reference textbook. Please refer this and try to solve this. If you don't get any of these questions, please try to contact me as well. So I hope you understood. Thank you.